So now we are going to look at the types of isomers that are being categorized under the geometrical isomer. So we have actually three types of geometrical isomer. One is actually first is cis and trans, which is the most common, and B we have E and Z, and C we have sin and anti. So we wanna look deep into the cis trans E Z and sin anti. So now first of all we are going dig into deep of cis trans. What are the cis trans isomers? So in cis trans, at least one group should be common. At least one group should be common. One group should be common, and that is known as cis trans. Like we have C double bond C and Cn, Br, H and Cn. So here one group means here chlorine and here chlorine. These two groups, among these two groups are same. So that is known as when okay same, that is the condition for cis and trans isomer. So when they are relatively far, here it is relatively far, that is known as trans. Or when they are relatively close, like C and Cl and Br and Cl and H, they are relatively close, then it is known as cis. So trans is relatively far distance and cis is relatively close distance. If you take some more examples, like we have C double bond C, H, Br and Cl and Cn. So whether it is cis or trans, no, it is not the geometrical isomer, because the basic condition must be satisfying that both these two groups should be same. Okay, that is known as geometrical isomer. Now if we talk about C double bond C and H and Cl and Cl and CH3, whether it is cis or trans, it is trans, because we convert the odd number of group into odd number of double bond into single number of double bond. We have seen already, it is like the alene system. Okay, it is alene system, right? Now we're gonna look the third compound one. This is an O. Okay, so in this third compound we have these two groups, similar group, are at the further distance of each other. So it is the trans. So it is a trans, right? Now there is something, some physical property of cis and trans, of physical properties. So how the physical property they do have? So like C double bond C and CH3, H and CH3 and H. It has dipole moment 0, because the dipole moment is going this side, and this side and this side. So net dipole moment is 0. Now what is dipole moment? How do we calculate it? We're gonna learn it in the, we have learned already in chemical bonding. So the dipole moment is 0. So boiling point is always directly proportional to the dipole moment, right? Now if we talk about the trans, this is trans. Now if we talk about the cis, here dipole moment is not 0. How it is not 0? It is going in this direction, summing up, adding up. Okay, right? And it is going in this direction and this direction. So net dipole moment is, we are not calculating the direction. We know that the summation of the net direction of these, the net vector of these two and these two are not equal. So there must be a somewhere net dipole moment, right? So boiling point directly proportional to mu. So mu is of cis here is greater than trans. So we will calculate mu of cis is greater than trans. So boiling point of cis will be greater than trans. More the value of dipole moment, more is the value of boiling point, because dipole moment attracts the molecule. We have because it gives the polarity to the molecule, and it attracts the two different molecule, which if two molecules are attracting each other, then the probability of going the molecule above the surface, the boiling point increases. You can simply say boiling point increases. So boiling point of cis is greater than boiling point of trans. Now when boiling point of cis is greater than boiling point of, but what about melting point? This is very important. Melting point. Melting point of trans will always be greater than cis. This is very important. Always. Whether it is boiling point, whether it is dipole moment, doesn't affect that, because in melting point what happens in melting point depends on lattice structure. Melting point depends on lattice structure. So when we talk about the lattice structure, we have when we talk about trans, how the trans does in lattice structure, one compound is this, another is this, one this. If we have a second molecule, this and this type of structure do we have. Third molecule, this and this, and fourth molecule. So this type of arranged structure. Arranged structure. So when we talk about the cis compound, it do not have arranged structure. Somehow like this is one cis. Okay, then it is another compound. This is cis. Okay. Now this is another compound. This is cis. This is another compound. This is cis. So this is a cis. It is a relatively less arranged structure. So more arranged structure, closely packed. It is closely packed. So when it is closely packed, its melting point of trans is always greater than C, irrespective of the dipole moment. But boiling point depends on the dipole moment, right? So like if I write some more examples, we have Cl and C double bond C and Cl and CH3 and a Cl, C double bond C and Cl and Cl and CH3 and H. So this is going in this direction and this is going in this direction, right? This is H. So the and here it is going in this direction. And so if we say that the melting point, here we have cis and here we have trans. So this is going in this direction and this is going in this direction, right? And the vector is going in this direction. And here the vector is going in this direction, right? So cis is greater than trans. The overall addition, the net dipole moment of cis is greater than trans. Because if we take the net vector, we have learned in physics the vector calculation, vector addition. So you can simply say that the cis is greater than trans. And boiling point is also cis is greater than trans. But melting point is trans is always greater than cis. Let's take one more example. We have C double bond C, Cl, and CH3 and CH3. We have one more C double bond C, Cl, and CH3 and CH3. Here dipole moment is 0 and here it is cis and here it is trans. So mu of cis is greater than trans. Boiling point of cis is greater than trans. Melting point of trans is greater than cis. Okay, this is a melting point of trans greater than cis. Now let's take some more examples. Let's take one more example. Means we have C double bond C H Cl and CH3. This vector is going in this direction and this vector is going in this direction. C double bond C H Cl H and CH3. Here it is Cl. So this vector is going in this direction and this vector is going in this direction. This is trans and this is cis. So mu of trans is greater than cis. Not always mu of cis is greater than trans. Mu of trans could be greater than cis also. So this is not a general statement that the dipole moment of cis is greater than trans. No, it is not always true. And it is not a generalized statement. But boiling point, here it is trans is greater than cis. But melting point of trans is always greater than cis. Now second we're going to talk about the EZ system. EZ system. For EZ system, we need to know the CIP rule. Now what is the EZ system? When all four groups are different. When all four groups are different, then there must be some naming. Okay, there must be some naming. We call it as a cis and trans, E and Z. Okay, so C double bond C, B, R, I, H, and Cl. And we talk about C double bond C, I, B, R, again H and Cl. So these two are different. These two are GIs, right? But how could we name which? How can I pronounce the first GI, and what should I pronounce the second GI? So according to that, when we have a compound like C double bond A, B, C, D, we have all four compounds are different. Then how do we pronounce? So we do the system naming ZE system, or we could say EZ system. Why do I call ZE system? Because Z stands similar to like cis, and E stands similar to like trans. Not similar to, not exactly same. Okay, right. Now why I call it as a ZEZ, not EZ, because it is similar to cis and trans. Just my trick. Okay. For understanding that we need to learn a CIP rule. CIP stands for Khan in gold pre-long. CIP rule. So what actually the CIP rule? Actually we give its naming. We give priority to this side and priority to this side. If priority 1 and 2, if priority 1 and 2, then come out that is called the Z, because it is a cis-like structure, because two similar compounds are on the relatively less distance, so it is like cis-like structure. But how do we give that priority? To give that priority we need to learn the CIP rule, Khan, Ingord and Prelong. So what is CIP rule? According to CIP rule, we first assign the priorities. Assign priorities. So how do we assign the priorities? To assign the priority, we give the priority directly proportional to the atomic number of atom attached. Why do we call the atomic number? We call the atomic number like uh, atomic number of the atom attached. Like if I take the example C double bond C, B, R, I, H, and Cl. And here we have C double bond C, B, R, I, Cl, and H. So atomic number here of iodine is 1 and bromine is 2. Chlorine is 1 and I is 2. So that is Z. And iodine is 1, bromine is 2. Iodine, chlorine is 1, hydrogen is 2. So it is A. Z stands for zusamine and E stands for antigen. That's just name, zusamine and antigen. We are not going to the meaning of this. Okay. So because these are the same side, so it is Z. These 1 and 1, or we can say 2 or 2 are different side, we call it as a E. And this was the rule 1. Rule 1. So we are going according to the rule. Next we have rule 2. Rule 2. What is rule 2? Rule 2 is like we have OH, C double bond C, H, OH. Here we have isotope 18 and here we have D. So whether it is Z or E, we have atomic mass are same, atomic number are same. So when atomic number is same, the priority is given to atomic mass. Priority is given to the atomic mass. So atomic mass of D is 1 and 2. Here it is 1 and 2. So which have the more priority atomic mass, we will give the priority to the 1. Right. So that's how we will naming it. And we have if we take one more example like C double bond C, and we have CH3 and C14H3, and we have H2N15, and we have H2N. Now the priority is to 1 and 2 and 1 and 2, so it is E. Right. So first of all, check the atomic mass, atomic number. If atomic number is same, then check the atomic mass. Correct. That was the rule 2. So what is rule 3 now? Now I'm not writing the side group, I'm writing the group directly itself, right? Like we have two groups, CH2 Cl and CH2F. So which has the more priority? The CH2Cl has one priority and CH2F the second priority. How? Because we will gonna see H and Cl, H and Cl. That's how these groups are. Okay, so first we go to the carbon. When carbon is same, now we go to the other three compound. We will writing in an increasing order of their atomic mass. H and Cl. Here we have H and, oh sorry, here we have F. Here we have F. H and F. So we're gonna check the priority. 1 same, 2 and 2 dash are same, 3 and 3 dash are different, and more priority given to the 3. That's how we have given the priority here 1, and here we have priority 2. So first just check the directly attached carbon, directly attached atom, that is carbon. Carbon is same. Now check their valencies. If valencies are different, priority to the valency are different, then the compound must be different. The priority will decide according to that. Okay, now we have a compound like CH2F and CH2 CH2Cl. Now CH2F, CH, H and F. Now CH2Cl, we have C, H, H, C, H, H and Cl. So how we will give the priority? We will give the priority. Here first we go to the carbon. We have went to the carbon. Now we have went to the carbon. Now we have H, H and F. Here we have H, H and carbon. Now, okay, the third one, here it is hydrogen, 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 hydrogen. Here we have carbon and here we have fluorine. So that's how we're gonna check. Okay, so which has more priority? The atomic mass of fluorine is greater than the carbon. So we will give the priority to the one to the this and second to the this. We will not count that whole one. We will go to the step by step, right? Fluorine, hydrogen are same, then we go to the fluorine and we got the carbon. If it was also the carbon, then we will go its valencies. Okay, that's how we go further. So I hope you are getting it. So now we let's look one more example. We have CH2 and CH2Br. Okay, and we have CH2 and Cl. Obviously CH2Br is more priority, and we have CH2F. Now we have CH2F and CHF and CH3. So now which has the more priority? Here we have hydrogen, then carbon. Here we have hydrogen, fluorine, then carbon. So now the fluorine and hydrogen is same. Now we go to the hydrogen and fluorine. Fluorine is both, so the priority to the the hydrogen, fluorine and carbon. So the priority carbon. So the priority to the hydrogen, carbon and hydrogen, fluorine, carbon. Its priority is more. Now look some more different type of compound, like we have this compound and we have this compound. So which has more priority? Obviously when we go to the first of all we will go the direction where we found the different group. One is oxygen, one is carbon. So here we found the difference, so we will give the priority to the direct first group. Okay, so we're gonna look these type of examples a lot. We have that two oxygen over here, and we have two oxygen apart from here. Now first we have oxygen, first we have carbon. First we will check the direction where we first find the difference. We could also go below carbon, but we are going to the above carbon because we are first finding the difference here. I'm talking about the previous example. Here it is symmetrical, so we will find the same answer from the both side, right? And when we go to the next compound, so we have this compound and we have sulfur. Now first carbon carbon, second oxygen, second sulfur. So if we got the difference, now this is the priority. So that's how we're gonna look the more compounds. So we have nitrogen, hydrogen. Okay, this now we have next oxygen, and we have now first is we have carbon, and first we are getting oxygen. So this is the priority. This is important. By first look, we thought that this is, we think that this is the answer, but the answer is this one, because the first group here is carbon, first group here is oxygen. We are not looking at the whole compound at the once. We go step by step, right? Now we have rule number 4. Now we have rule number 4. C triple bond and N CH2 NH2. C triple bond and CH2 NH2. Now we convert that into the, how can we compare? One, we have that three different valency. Here we have three same valency. So we will convert C triple bond N into C N N and one valency connected to the carbon, another. So we will open the valency, right? How we open the valency? Carbon, we have 3 bond, 1 2 3, apart from this group. Okay, 1 2 3, all 3 connected to the nitrogen. So we added nitrogen, nitrogen and nitrogen. So these two hypothetical bonds are added, and nitrogen we have added to the carbon and carbon, right? Because nitrogen, all the 3 bonds are connected with the carbon. So now we check. Here we have nitrogen, nitrogen and nitrogen. Here we have hydrogen, hydrogen and nitrogen. So obviously this one has the more priority. So we have more groups, and we have more questions to do. So that's we gonna do in the geometrical isomer third part.